Welcome back, folks. We're going to take a look at, or we're actually just now getting into Unit 5 now, which deals with light and the behavior of electrons and electron configuration, all kinds of fun stuff. So the first thing that we want to take a look at is light, because we've actually learned a lot about chemistry through light. Okay, now light actually is going to have, excuse me, it's like a split personality basically. Light can behave two different ways. Number one, it can behave as a wave. Okay, so it can behave as like one of those little waves. It moves across wherever. Okay, however, it can also act as a particle. Okay, and so if it's acting as a particle, we would call it a photon, and we're going to get to that in a little while. Now, if we're looking at light as a wave, we need to focus on three things. Number one, that wave has a speed. Okay, what is the speed of a light wave? Well, the speed of light was figured out a long time ago, and it is probably the most well, it says it's the most accurately known constant in the universe. Okay, and we call it c. Okay, you've heard of E equals mc squared. Okay, well, the c is the speed of light. Okay, and so we call the speed of light, we can measure that as 3.0 times 10 to the 8 meters per second. Okay, now a lot of what we do is going to deal in nanometers. So what we can actually do is we can also memorize this term right here, which is 3.0 times 10 to the 17th nanometers per second. Now you're going to be given this value on a test or a quiz. Okay, you're going to be given that value, and if you need to convert meters to nanometers, you can use your information back from Unit 2, dimensional analysis, to do that. Or you can just go ahead and memorize that 3.0 times 10 to the 17th nanometers per second is the same thing. Okay, so that's the speed of light. That is c. All right, so now let's go ahead and take a look at what wavelength is. Wavelength is characterized by the Greek letter of lambda, and lambda looks like it looks like this little fella right here. Okay, it looks like a little upside down Y, and so that's lambda. It refers to the length of a wave, so we can see right here. Here's two different waves. This one's going to have a longer wavelength. Okay, you're going to measure length from either crest to crest or trough to trough. Okay, so this one's going from crest to crest, which would be the same thing. That's the length of the wave. That's how long the wave is. Okay, notice the bottom one has a shorter wavelength. Okay, so the crests are closer together, giving it a shorter wavelength. Um, and lastly, we have the frequency. It's represented by the Greek letter nu, which looks like a V. Okay, in fact, most of the time I'm going to be lazy and I'm just going to call it V. Okay, to be most correct, it's a nu, but nonetheless, we can also call it V because it looks like a V. And this is the number of times that a crest is going to pass a given point in 1 second. Okay, or really in any amount of time. Okay, so if I were to draw a line right here, okay, if I were to draw a line right here, and both of these waves are going this direction, okay, which one's going to have a greater frequency? Which one's going to have more crests past this given point in a given amount of time? Well, of course, the bottom one will, because it has a shorter wavelength. So now we can say, okay, when we have a shorter wavelength, we have a greater frequency. So those two things are inversely proportional, okay? So let's go ahead and keep on looking down here. This is the electromagnetic spectrum. And the electromagnetic spectrum gives us an idea of the energy that is associated with different lengths of waves, okay? So when I look here at radio waves are going to have a very long wavelength, okay? So, and let's also think about this for a second. Let's look at a long wavelength with a long flowy wave, and then let's look at this one with a really short wavelength, okay? Just by looking at these, can we guess which one has more energy? Okay, one of them looks like it's nice and relaxed, and the other one looks like it's real angry and real rough. Okay, the one that looks real angry and rough, of course, is going to have a greater amount of energy. So now we know that if we have a long wavelength, it's going to have a low frequency and it's going to have a low amount of energy. Whereas if we have a short wavelength, it's going to have a high frequency and it's going to have a lot of energy. Okay, so that is what we need to understand about waves and wavelength. So let's look at this. Basically, this chart right here goes from the longer wavelengths, okay, and then the wavelengths are going to start to get shorter and shorter, Then they're going to start to get even shorter and shorter and shorter, and then they're going to start to get really, really, really short down here. Okay, so that means that gamma rays are going to have the highest energy, the shortest wavelength, and the highest frequency, whereas radio waves are going to have the lowest energy, the longest wavelength, and the lowest frequency. And right here in the middle is where we would find our visible light spectrum. Now, you do need to be aware of this situation here. Okay, and here's this little you can use this little mnemonic device down here if you'd like. But either way, radio waves are the longest, then microwaves are a little shorter, then infrared, then your visible light spectrum, which is going to include Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And then after a violet, you get to ultraviolet, X-ray, and then gamma rays. Okay, so that's the order that we go in for our different wavelengths. So just kind of work with that, get an idea of what's going on there. The fact that radio waves don't have a lot of energy, they're very long wavelengths as opposed to gamma rays. And then you've got visible light spectrum right in the middle. Now, check this out. I've got red, which bumps right up next to infrared. Okay, so if I were to ask which one has more energy, the red is going to have more energy because it's closer to gamma rays. Infrared is closer to radio waves, so it's going to have a lower energy. Okay, if I were to ask you what color had the highest energy, you would tell me that violet has the highest energy because it's closer to ultraviolet. Now, the actual wavelengths of these is red is 700 nanometers and violet is 400 nanometers, and all the other colors fall somewhere in between there in terms of their wavelength. So we're still talking about small lengths, okay, short lengths. We're talking about nanometers here, but red is going to release light at 700 nanometers, and violet's going to release light at 400 nanometers. Anything shorter than that is going to be ultraviolet or shorter, which is not something that our eyes can detect. Anything longer than that is also infrared and beyond. So that's also things that our eyes cannot detect. Our eye can only detect this light range right here. Okay, so I will go ahead and scroll down to here so that you can see these two answers. Think about these a little bit. I've already mentioned the first one. Think about those a little bit, and we'll see you in the next video.